Hi, my name is Lambrix. I'm going to talk about work together with my colleague Niklas Carlsson on goal-based performance measures. Before I start with the actual topic, I will tell you the true story of how we started with hockey analytics. For Niklas, this motivation started a long time ago when he started, just like many others, dreaming of the Stanley Cup. And he gave it a good try. He played hockey both in Sweden and in Canada. Didn't make it to the NHL, but he did get a PhD. So he gave it a second try, and this time he actually just went to visit the Stanley Cup. It was a bit easier, and considering the smile that we see on this slide, it shows that this was very rewarding as well. I'm not sure he has completely given up yet because he's still playing hockey. But the next step then is, of course, that when he has reached the Stanley Cup himself, how can we help teams reach this Stanley Cup? For myself, it's a much easier motivation. I do like to watch sports, in particular ice hockey. It can be a bit much, but since I've been working on sports analytics, whenever I watch a game, I can tell my wife that, I'm actually working. And that seems to do the trick. So let's go to the motivation for this talk. For this crowd, I don't really need to go into these traditional performance metrics. Throughout the talk, we will talk about goals, assists, points, and plus minus. But this did give me an excuse to have a slide with Brock Little at the top. New metrics are introduced every now and then, and there are good reasons. For instance, Corsi, which is shot-based metric, was introduced because it's a better predictor for future goal differential than actual goal differential. Now, we also have to be aware of the fact that whenever we introduce new metrics, they may actually influence the game. So for instance, players may start shooting from wherever on the rink. Their Corsi will go up, but it's not necessarily the case that this is a good thing for the team. And expected goals tries to deal with this. It assigns a value to each shot based on the likelihood of the shot resulting in a goal. Also, quite a lot of different game scores have appeared the recent years, and all these metrics have now made it into the ice hockey discourse. Now, a critique that is often heard is that they don't take context too much into account. Some do a little bit like expected goals. For instance, it does take into account shot location, but more could be done. And Oliver Schulte has talked, for instance, about Markov games in his lecture during LINHAC. And he also showed Tor during his lecture. So what we want to do is to introduce some metrics which are goal-based that take account the context. We look at two different variants. The first kind of variants are variants of traditional metrics, the ideas that are easy to understand for practitioners, for players, and they're going to take into account the importance of goals. And the second kind of metrics are new advanced metrics, where we work further on the work by Oliver Schulte, and we take into account actions leading to goals. So let's look at the methods and results. The data that we use is play-by-play data from Sportlogic. It's relatively old data from the 2007-2008 season to the 2013-2014 season. And in this talk, I will only talk about the regular season. So let's look at this first variant. Now, when we're going to define a metric, there are some questions that we should ask ourselves. The first one is, what are the intuitions behind the metric? Why is that we will need exactly this kind of metric? What is new? Then we have to properly define the metric. And then comes the tricky part of evaluating a metric. We don't have a gold standard, so people need to have a work around that. And what they usually do is, first of all, they check whether it passes the eye test. Do the players that you expect to be high up in the ranking according to this new metric actually end up there? You also want to check whether there are correlations with existing metrics. You don't want to have a perfect correlation because then it's just the old metric. You want to get something new, but it's still good that there are correlations to metrics that people have agreed upon within the field. You also want to check whether the metric is stable over seasons. And an interesting question is whether you can predict the value of the metric at the end of the season based on data for part of the season. So for instance, after half of the season, can you predict what the value would be at the end of the season? So let's look at the first question. And we'll start by looking at a few observations. So a first observation is that the number of goals that are scored in each minute of the game are pretty evenly distributed, except for the first minute where very few goals are scored, and the last minute where actually 3 times more goals are scored than in any other minute of the game. One possible explanation is, of course, that there may be quite some empty net goals. Another observation is that goals are not equally important in terms of winning or tying a game. If you are scoring a goal leading to the 6-0, then the sixth goal may not be that important in terms of winning the game. You probably would have gotten the points anyhow. However, when you score a goal in the last minute, breaking a tie, then the probability of winning this game is going to be quite a bit higher. So I had the advantage and privilege to listen to Oliver Scholz's recording before LINHAC. And I'm going to connect back to some of the terminology that he used. He used success for an outcome that a team wants to bring about. Could be winning a game, could be scoring a goal. He also showed example of success probability tickers using a figure from Pettigrew, where we see a game between the Flyers and the Stars. And what is depicted is the win probability over time. And what he remarked upon was that this win probability changes usually most drastically whenever goals are scored. And this is something that we are going to use in our work. So success are going to be game points. These are the 2 points that you get for a win in the NHL and the 1 point for an overtime loss. And use game points to distinguish them from the points that are really goals plus assists. Then we have success probability tickers, which are going to be based on goal events. And we're going to look at the difference in success probability, so getting game points, immediately before and after a goal. So it's going to tell us the influence of a particular goal in receiving game points. So we're going to look at outcomes in regulation time, which can be wins, ties, or losses. We're going to look at context, and a context is defined using a time, which we will look at in seconds. A goal differential, so for instance, if the score is 5-3, then the goal differential is +2. And the manpower differential, which can be even strength or power play 1 or 2 or shorthanded 1 or 2. And then we're going to look at the probability of an outcome given a context. So for instance, the probability of winning the game, given that we are 10 seconds before the end of the game with a goal differential of +1 and a manpower differential of 0. And we're going to define this as the number of times that this context occurred given the outcome. So the number of times this context occurred given that we actually won the game, divided by the number of times that this context occurred. And we're going to use these probabilities now for assigning an importance value for a goal in a particular context. So the context in the formula is the same as the context just before the goal. So BG stands for before goal. We also have a context AG after the goal, immediately after the goal is scored. We're going to define it as follows. First of all, we're going to look at the difference between the probability of winning, given the context immediately after the goal, and the probability of winning, given the context immediately before the goal. So it actually gives us the change of probability of winning this game by scoring this goal. And similarly, we can look at the change of the probability of the game ending in a tie by scoring this goal. And then we're going to weigh these probabilities, or the differences in probabilities. For winning, we get 2 points, so we set a 2 there, and for tying, we get 1 point. So we set a 1 for the change of probability of the game ending in a tie. We sum these up, and this gives us the importance value for this goal. So let's look at some characteristics of this game point importance value. Here we have plotted it against the goal differential. The darker the green, the more important the goal is. And the darker the red, the less important the goal is. Actually, when the color is red, we actually have a negative importance. And we see that in this case, we do have a negative importance when a goal is scored early in the game and the goal differential is 2. So for instance, you're leading with 2-0, you score at 3-0 early in the game, that goal may actually have a negative importance. This is data from the 2013-2014 season. We also see that the darker green is usually at the end of the period, of the third period, where we see that if the goal differential is -1 and a goal is scored, then of course we're going from -1 to 0. That means that we're tying the game. So this is an important game, an important goal. And we also see a bit darker green when the goal differential is +1. So scoring a goal there gives us a +2 goal differential, and that makes it almost sure that you will win the game. If we plot it against manpower differential, so even strength or power play shorthanded, there's not so much difference in the importance over time as for the goal differential, except that we see some major things happening when you are shorthanded with 2, so 5 against 3 situations. When we look at the cumulative distribution function of this value, we see that about 0.02% actually has a negative importance value. So not too many goals are given negative importance, but some do. About 82% of the values are between 0 and 1.5, and 18% of the goals get an importance value between 0.5 and 1.64. And this is also shown in this plot, where we have first even strength, then power play, and then shorthanded. You see that most of the goals will have an importance value between 0 and 1.5 for each of the different manpower differentials. So how are the metrics now defined? We're going to use this game point importance value. And if you look at the traditional metrics of goals, assists, points, and plus minus, whenever a goal is scored, this goal contributes directly or indirectly the value of 1. So the goal scorer get a +1 for the goal. The person that gave assist or the second assist get a +1 for the assist. And all people on the ice also got a +1. In the same team got a +1 for the plus minus. So a goal contributes 1 in each of these metrics. So what we're going to do now is we're going to use variance of these metrics, where a goal contributes with a context-based game points importance value. So it's not just going to be contributing 1, but it could be a negative value, or it could be a value for the season that we looked at up to 1.64, but usually between 0 and a half. Now, what does it mean? It means that these new metrics will combine still the number of goals in which the player is involved, but also the importance of the goals in which the player is involved, and importance based on what the influence is for getting game points. So does it pass the eye test? Here we have the top 10 players for the points. We have similar rankings for the other metrics, but for the sake of time, I will only look at the points here. We see the players ranked according to this new metric. And in the first column, we see the rank according to the traditional points. We see that Sidney Crosby is first on this new ranking, and it used to be on rank 2-3 for the traditional points. It says 2-3 because there were 2 players which had 69 points there. When we look a bit closer to the rank differences, we see that Ovechkin has gone up in the ranking compared to the traditional points. And this makes sense. He was actually the top player during that season in game-tying goals and lead-taking goals. So these are important goals that are scored for getting game points. At the same time, he was only 29th in the ranking while scoring when the team was already in the lead. Other people that were raising quite well in the rankings are the places number 8, 9, and 10. And these are players that are known for stepping on when the games become tougher. You could say that these people are game-changing players. So you could say that, yes, this passes the eye test, and this does give something else than the actual points. So are there correlations with the existing metrics? So let's look at the points again. First, we can look at the rankings. What we have plotted is at the x-axis, we have the traditional rank, so the traditional points, and at the y-axis, we have the rank according to the new kind of points, the importance-based points. Then the people who are on the black line, they are the ones that keep the same ranking. The players that are in red, they have reduced their ranking, and the players in green have improved their ranking. So we do see that this new ranking with the new kind of points is not exactly the same as the traditional points. And this is one of the things that we want. We want to have a different view over the players using their points. However, it's nice that there still is a correlation. And that is also something that we see here. If you look at the different seasons, we do see that there's quite a nice correlation between the traditional points and these importance-based points. It is a little bit less for plus minus. For assists and goals, it is very similar to the points. Here we show the correlation between the traditional points and the new points using 3 different correlation measures, the MIC, the Pearson, and the Spearman correlations. The yellow dots show the correlations as I've shown in the previous slides. And for the points, for instance, the correlation is between 0.94 and 0.97. So it's quite a high correlation. The correlation becomes even higher if you look at the blue dots. And what we've done here is we have removed the events that occur less than 10 times. And in that case, these outliers are gone and the correlations are even stronger. So what we have is strongly correlated measures for goals, points, assists. but still not exactly the same. So it gives a little bit different view at things. So is the metric stable? And here we look at different seasons. So what we do see is that over all seasons, we have a maximum for the new kind of goals, assists, and points, just we have for the traditional ones. And this value goes down to a few players which actually have minus values. But if we look at the maximum values for these metrics during all these seasons, we see, for instance, for the goals in this, that the highest scoring was 63 in the 2007-2008 season, and the important base goals got a score of 19.546. There is a difference between the maximum value for the goals over the different season, and the maximum value for the importance-based goals kind of follows this trend. So I would say that the trend is the same, so we're quite happy about this. You see there are also some notes there, 1 to 8, and these are places where the player that had the highest rank for the traditional metric and the player that had the highest rank for the new metric were not the same. So for instance, if we look at the note number 1, we had Corey Perry, who scored 48 goals, but he did not have the highest importance-based goal rank. That one was for Daniel Sedin, who only scored 41 goals, but his game points important value was 13.098. If you look at the list of these notes, the players that are on the left-hand side are actually the ones that lose in the ranking if we look at importance-based goals instead of ordinary goals. And the players that are on the right-hand side are the ones that are winning in this ranking. So for instance, Henrik Sedin scored lots of goals, lots of assists, but actually lost several times in the ranking if you look at the importance of these goals and assists. While players such as Crosby and Ovechkin scored a bit less goals, assists, but when you look at importance, they go up in the rankings. Another interesting thing is, can one predict the value of the metric at the end of the season based on data for part of the season? And that is what we look at here. So we have partitioned the data into 2, 4, 6, 8, and 10 partitions. So when we have 2 partitions, what we do is we look at for instance, the number of goals that are scored after half of the season, and we multiply this by 2 and compare with the actual result at the end of the season. We do this for all the players, and we measure the correlation. If we have 10 partitions, we would take the goals after 1/10 of the season, multiply by 10, compare with the actual result, and do for all players and measure the correlation. So what should we expect? Well, of course, for 2 partitions, you have data for half of the season. That is much more data for if you have 10 partitions when you only have 1/10 of the season. So you would expect that the correlation goes down. And this is exactly what we found. If we compare the red and the orange bars for the different seasons, these are showing us actually, the red shows us the results for the traditional assists, goals, points. And the orange one gives us the correlations for the new kinds of the important-based kinds of points, goals, and assists. And we see that when we have the values for half of the season, both actually are pretty good predictors for what the end result will be. If you have more and more partitions, then it's a little bit easier for the traditional measures to predict what the end result will be than for the new measures. But I think we can be happy with the fact that they're quite similar for for a smaller number of partitions, and that you can actually say something after half of a season. So currently we are working on also introducing playoffs and looking at the overtime goals. So let's look at the second variant. I'm actually going to introduce Oliver Schulte's work from 2015. This is what we worked on. And of course, he has more extended models since then. I like his Ichkai 2018 paper a lot, where he introduced this GIM approach, which showed correlations to many of the traditional performance metrics. But the idea here is to define states, where a state has a context and a play sequence. You perform actions in the state, then you define the impact of an action in the state, and you define the player impact based on these action impacts. So in this 2015 model, the context had three parts: a goal differential, a manpower differential, and which period. And it had a number of events, which could be action events like face-off shots, and start and end events like the end and start of a period, or when a penalty was given, and so on. In his newer work, he has many more events, and context is also a bit more specific than here. A play sequence can then or be the empty sequence or the sequence of events. You always have a start marker, a first event, and then you can add to these events. You can have a next event, which is an action event, and you can have several action events, and you could have an end event as well, which is then the last event in the sequence. And if you have an end event, it's called a complete sequence. And this allows you to build up such a tree, and I'm going to pick out some nodes in this tree. So in the first node on the top, we have a state where we have a context, where the goal differential is 0, the manpower differential is 0, and we're on the first period. And we have an empty play sequence, so nothing has happened yet. In the second node, we have the same context, but quite some events have happened. It started with a face-off, and then there were some other events, and it ended with a goal by the home team. Now you can perform actions in these states, and you go from one state by performing an action to the next state. And this next state is then defined by, well, if the state didn't have an end event, then you just add the action to your play sequence. So for instance, I have done already a certain play sequence. Now I do a shot. So I just add the shot to the play sequence I had. And if the state had an end event, then the context may change. So for instance, if I scored a goal, then the goal differential will change. And the next state will start with an empty play sequence. Then we're going to look at how often these sequences actually occur in our data. So we will denote by OCC of S, the number of times state S occurred. And we're also going to look at the number of times that state S was immediately followed by state S prime. And then the transition probability is then the number of occurrences of S immediately followed by S prime divided by the number of occurrences of S. So for instance, I could be in a state, and in that state, 80% of the time I take a shot, and 20% of the time I give a pass. So these 80% and 20% would be my transition probabilities. So this is also denoted in the tree, where you see in the squares, you have the occurrences in the states, and in the ovals you have the occurrences of one state being immediately followed by another state. And then we're going to calculate Q values. Q values are values that try to give some reward to actions that lead up to a state that you really want. So in this case, we want goals, and a goal state receives a reward of 1, and these Q values are going to somehow give some of the reward to actions leading up to scoring a goal. This is the algorithm that they use, but I'm just going to pick out the main statement in the algorithm. This is how these Q values are computed. We have different iterations. So in the I+1 iteration, the Q value for a state is computed as follows. We look at the reward for the state. So if you have a goal state, your reward is 1, otherwise it will be 0. And then we're going to look at the states that we can reach from our state. Now, if we move the 1 divided by the occurrences of S into the sum, then we actually get the transition probability there. So it's essentially a sum of the transition probabilities times the states, the Q values of the states S prime. So for instance, what I would do is if I have 80% of the time I take a shot and I had a Q value of 2, then I would say, okay, I take 80% times 2. 20% of the time I would give a pass. I had a Q value of 1, so then I would have 20% times 1. So I have 0.8 times 2 plus 0.1 times 1. This will be the sum that I have there. So it gives you a chance to distribute some of this reward for scoring a goal to the actions that were leading up to this goal. And then we're going to look at the impact of an action in a state, so an impact of the shot or impact of the pass. And this is going to be defined as the difference of the Q value of the state after the shot or the pass and the state before the shot or the pass. And also these things are in this tree. So we see the reward functions in blue, where non-goal states had a 0 value and goal states had a 1 as a value. And the algorithm has computed a number of Q values. And the impact of an action then is the difference in the Q values from one state to the other state. So once you've defined the action impacts, you can define the impact of players. And what Oliver Schulte did in his early paper was he has based the impact of a player on all the actions that were performed by that player. We call this the direct goal-based impact. But you can also have a kind of like a plus-minus variant where you also give credit to the players that were in the ice. And the idea is that, okay, maybe somebody scores a goal, but this player had an open shot possibility because another player has drawn away a defender. So we also give some credit to this player who drew away the defender. And this we call then the on-ice goal-based impact. And you can also have variance normalized by time. Now, using these action impacts, you can actually also look at player pairs by looking at the sum of the impacts when both players are on the ice. We call this the on-ice goal-based impact. So what can you do with this? Well, here we have a ranking for the top players in the 2007-8 and 2008-9 seasons for the direct impact. Again, this passes the eye test. The players that are high up in these rankings are players that are high up also in the goals rankings, the traditional goal rankings, and the traditional point rankings. If we look at the on-ice impact, also here these make sense. You do see that there are many more defenders higher up in these rankings, and this has, of course, to do with the fact that defenders play much more. They are on the ice much higher amount of time. You could plot the different performance metrics with respect to the salaries. So for instance, if we look at the traditional goals, the first column is for defenders. Here we're forwards, here we have goalkeepers. Goalkeepers, this doesn't make sense. But for forwards, you see that for the same salary, there are actually quite a lot of different goals scored by different players. And in general, when the salary gets higher, the number of goals tend to get higher as well. The direct impact gives a bit similar picture, but a little bit more varied. Now, some work that we have done then was about looking at different pairs. For defenders, this makes sense. You usually talk about defender pairs. You would like to talk about forward lines, but there's not as much data for 3 players together than for 2 players, so we've looked mainly at pairs. We also included mixed pairs, so 1 defender with 1 forward. And what we see is that, again, this kind of satisfies the eye test. We do see that many of the top pairs that we find using these metrics are players that are also high in the joint time on ice. And this indicates that these are the players or the pairs of players that the coaches give a lot of credit to, that the coaches use a lot and rely upon a lot. For the people that are fans for Linköping Hockey Club, we do recognize 1 ex-player. We can have a look at the impact per minute for these pairs. We have the 2 different seasons in different colors here. What we see is that the variation decreases the more time on ice together is spent. And this is normal. If you have only a few minutes on ice together over a season, then it can just be luck that a goal was scored when you were on the ice, or the opponent scored goal when you're on the ice, and you don't have much time to do something else about this. The medians are the highest between 16 and 256 minutes of joint time on ice, and then it drops a bit. This could be because players are a bit more tired maybe, but most probably these are the players that are relied upon the most and have to play against the toughest opponents. And therefore the impact goes down a little bit. Now here we have plotted the impact per minute versus the time on ice together. And the different colors are now the different kinds of pairs. So the red ones are the forward pairs, the green ones, defender pairs, and the blue ones, the mixed pairs. And maybe what is interesting to see here is that, well, on TV, we always hear about the defender pairs and the forward lines, but it looks like the impact here for the mixed pairs may actually be higher than for the other kinds of pairs. So maybe it's interesting to look at which defender and which forwards play together, instead of mainly looking at defender pairs or forward lines. So what we have done here now is we have introduced some new goal-based performance metrics for ice hockey players. We do see strong correlations between the goals, assists, points, between the new and traditional metrics. some correlation also for plus minus, but not as strong. And all of these pass the eye test. What we are working on now is combining these two variants by using the game point important values as the reward function in variant 2. So it's not the case anymore that a goal always gives a 1 there, but we're going to do reinforcement learning using the game points important value. We're also looking at alternative reward functions for the performance model and maybe learning these reward functions. And in some other work, we've also done some game prediction and season simulation. Most of this work has been done by having our master thesis and bachelor thesis students implement our IDs. And we want to thank these students. And we're very happy that from August, we will actually have one of these students who will come and work for us for several months. We'll finally have somebody who can full-time work with this kind of things. And if you want to read more about our work, we have our papers available at this page. That's it for this talk. Thank you very much for listening. And if there are any questions, we will take them in the Q&A. Thank you.